A basic reminder of inequalities. If you had two numbers, 7 and 5, if I wanted to say that 7 is greater than 5, I would face the symbol this direction. The big wide opening is facing the 7, that's the larger number, and the skinny point tip, the small part, is facing the smaller number, 5. If we reversed that so it looked like 5 compared to 7, we would have to turn the symbol around to show that 5 is smaller and 7 is wider or bigger. Now, how do we do that with a number line? If you look at this first example, we can see what's called a boundary point. The end of the shading is called the boundary point. So the number 5 is the boundary point. Because the number 5 is colored in, we can also be equal to the number 5. And if I look at the shading goes towards the left, and all of these are numbers that are smaller than or less than 5. So the way that we would write our answer is we would write all of these numbers, they're x's. Any x number has to be smaller than or equal to 5. Let's try another one. In the second number, the boundary point is here at -1. And again, it's shaded towards the less than, going backwards from -1. And so we'll write our response, our answer, as x could be any number that is smaller than 1. This time, because the 1 is not a colored in circle, it's called an open circle, we cannot put the equal to line. Problem 3. -1 is the boundary point. Oh, that was -1 on the last problem too. -1. Then, this time the numbers are shaded larger numbers than -1. So this time we would say x has to be a number that is bigger than -1 or greater than -1. But since it's not a colored in circle, it's an open circle at -1, we would say that this is not equal to. Last problem. The boundary point is at -5, and the shading is numbers that are less than or smaller than -5. So we would write that the x has to be less than -5, and because the boundary circle is colored in, we'll say that it could also be equal to. A common rule of thumb is, as long as your x is written first on the left-hand side, the direction of the inequality symbol matches the direction of the arrow. As long as the x came first, the direction of the inequality matches the direction of the arrow. Pointing to the right, pointing to the right. It's a helpful rule of thumb if you can't remember them. How can we use this idea of a boundary point and a number line to help us solve problems that have inequalities? So the words say solving linear inequalities with one variable. And I'm going to walk you through the process. So we're going to start with this first problem. 3 minus 2x is less than 1. So what we need to do is solve for x. Treat this just as an equal sign. 3 minus 2x is equal to 1. And then you're using your normal solving for x skills. You can put the line down the equals, and we can solve for x. Maybe you want to minus 3 on both sides. So you're left with -2x, and 1 minus 3 would be -2. Then to get the x by itself, we have to divide by -2. And so we'd get x equals +1. -2 divided by -2 is +1. This is what's called the boundary point. So that is part A. The key point is called the boundary point, so we solve for that. Part B, decide if the boundary point is part of the solution. If it is part of the solution, the number line has a filled in circle, and if it's not, it's an open circle. So we're going to draw a number line. 0, 1, 2, 3. Your number line can have any scale that you want, and then we just need to mark that boundary point was at 1. So we'll put an open circle at 1, and we check back to our original inequality. Since this does not have an equal to line on it, we have to keep the circle open. It is not actually equal to 1. That's just the boundary. From here, we have to decide if we should have the shading should be numbers larger than 1 or numbers less than 1. So the way that we do that is part C of the directions. Determine which side of the boundary point the solutions lie. Choose a point to test in the inequality. If the point is a solution, then all points on that side are a solution. So for example, let's try testing the point number 2. I could pick any point on here that's not the 1. If I go back to my original problem and I plug in that the x is going to be a 2, we'd have 3 minus 2, replace the x with 2, and we need to check, is that less than 1? 2 times 2 is 4, and 3 minus 4 is negative 1. So is negative 1 less than 1? Yes, that's true. So the side that we picked with the 2 is the correct direction to shade. All the numbers that are greater than 1, all numbers greater than 1 are solutions to this inequality. If we had tested a number from the number line and gotten a false, then we would have known that the other side is correct and we could have shaded the other side. Our goal is to solve for x, test a point on the boundary, finalize our number line shading, and write the final inequality that says x is greater than 1. I'll do one more example. First step is to just solve for the boundary point. That means treating your equation just like it would be a normal equation with an equal to. 3 minus 2, parentheses, n minus 4 is equal to negative 1. From here, anytime we see those parentheses, that means that this negative 2 needs to multiply by the 2 parts inside the parentheses. So we'll end up with negative 2n, and negative 2 times negative 4 is positive 8. And then we'll rewrite the 3, and the equals negative 1. Most students at this point will draw the line and notice that on the left they have numbers that are like terms that they can combine. So we can add 3 plus 8 and get 11 minus 2n equals negative 1. To try to get that n by itself, we can minus 11 on both sides. Negative 2n equals, oh boy, negative 12. And our last step would be to divide by negative 2, and we would get n equals negative 12 divided by negative 2 is positive 6. Now this is just the boundary point. It's not our final answer. So on our number line, we can make a circle for at 6. Then we check our original. We look at the inequality. Does it have an equal to line? This one does not, so we're going to keep the circle open. If it had a line under it for equal to, then we would color in the circle. Step number 3, test a side of the boundary point. We can pick any number to test in our inequality. For example, maybe we'll pick this number down here, 3. If 3 works, the inequality gets shaded this way. If 3 doesn't work, it shades the other way. So I'll go back to my original equation, 3 minus 2 parentheses. Instead of n minus 4, we're replacing the n with our test point, 3 minus 4. And we want to know, is that greater than negative 1? PEMDAS, inside the parentheses, if we multiply these, subtract these together, 3 minus 4, negative 1, multiplied by negative 2, would be positive 2, and then plus the 3 would make 5. And we're wondering, is 5 greater than negative 1? That is true. 5 is greater than negative 1. So our number line should be marked and shaded towards the 3. If we had gotten a false, then we would know that the number line should have instead been shaded the other direction. The number line is my visual, but I still need to write my final answer. 6 was the boundary point, so our choices for x, or for n, had to be numbers that are less than 6. The example point was 3, but 4, 5, and any other numbers less than 6 could have worked.